Good morning or good afternoon, everyone. This is the fourth part of our Julia series. And today we're going to talk about the parallel computing again. In our previous talks, we talked about the Julia and talked about the Julia parallel computing with the Julia and parallel computing with threads. And now today we're going to revisit some of the aspects of parallel processing that Julia offers. Okay, here's the outline, what we're going to cover and we were not going to cover. We're covered examples of using a parallel processing through a distributed package and through distributed arrays and shared arrays. And in the end, we will show example using the threads. We're not going to cover using Julia in Jupyter Notebook. I feel like that might be a little bit of extra work and it might distract some people. And we're not going to cover threaded computing details, which will be a separate talk, and I will leave it to my colleague at Armstrong for future presentation. And we're not going to cover MPI, or message passing interface, and others. This is not a tutorial, but rather a collection of pointers to some information for people to explore in your spare time. So first, running multiple processors, running Julia on multiple processors. So if you have a personal computer with a multi-cores nowadays, and many people have laptops and desktops that I have 4 or 8 cores, and some people might have 16 or 32 cores. And if you do have that many cores, then you can certainly run multiple processes on your personal computer. On your computer, you just type from a command line, you type a Julia -P with the number of cores or number of processes you want to start. And the other way to use multi-processes or running Julia on multi-cores is you start a Julia without option, and then inside the Julia, you use the command add procs and the bracket that you can put in a number of cores or number of processes you want. For example, here you put an A. This number can be greater than the number of physical cores you have. Basically, it just starts at 8 workers. Okay, 8 processes, and you can start 16 or 64 processes. But if you don't have that many cores, they could be just sharing the CPU. Okay. On clusters, you would have to use a machine file to tell Julia where you want to start your Julia processes. Here are some examples. If you're running a Julia with multiple processes on your personal computer, desktop, or laptop, and in the machine file, you can just simply put localhost and the slot equals number of cores you want. Or on the cluster, the machine file or host file will consist a list of nodes. For example, in this example, it shows I have a node. This is on on the cluster gram. 743,766, 622. And these nodes, I'm going to run Julia processes on these nodes in a synchronous manner, in a managed manner. If you're curious to know how to run Julia processes in parallel, which is supported by MPI underneath, Here is a sample job submission script. You define the number of tasks which correspond to the number of MPI ranks or MPI processes. And then you define your runtime, memory requirement, your group account, job name, and output, and so on. Everything is the same. The only thing different will be here, I use srun first to create the list of nodes, to create the host file. Okay, and so far this is the way to run the Julia on cluster with Slurm. So run srun first to generate the host file, because once the job submission script is executed, when your job starts, the Slurm return the allocated nodes. Now the information is all available. Then you run this srun. Srun will return the the host names allocated for your job, and then with that host name host file, then you put the line Julia machine file host file, and then run the Julia code using the number of workers or cores that you specify. Okay. Okay. So with distributed computing, there are two simple mechanisms one can use. One would use the two macros. One is the everywhere, and the other is spawn and the spawn at. Let's take a look at the example here. You're going to put the call using distributed. This is a package name, which supports the parallel processing on distributed memory system. And then what's happening here, I use the macro everywhere to define a variable 1, 2, 3, 4, 5 stored in X, and this defines the variable X on every processes. Okay. Now, if I define the X0 equals 1, 2, 3, 4, 5 from command line, this is local. Every variable defined by default is local to the current process, which is the main control process. And the X0 won't be visible on other processes. In order to have other processes have this variable X0, you would have to broadcast the values to other processes. So that's the typical operation in distributed or parallel computing. You broadcast your data to other processes. Now, if I simply put everywhere X equal to X0, and this will fail because X0 is local on the right-hand side. In order to broadcast this, define the, in order to broadcast the value to other processes, you need to refer to, on the right-hand side, you need to refer to the value of this local variable. To do that, you use a $sign. The $sign means I'm extracting, evaluating the value stored in this local variable X0, and then use this value and define the variable X everywhere on other processes. Okay, I'll show the example in just in a few moments. Next, this is we broadcast. We just showed we broadcasted a value, but now we can also broadcast, quote unquote, a function. And here again, I define a function show ID. This function show ID just displays the my ID returned by the Julia function my ID. Now this function is defined, if this function defined as a local function, okay. So this function is only visible to the current process or the main control process. If I say everywhere show ID, then this will fail because this function itself is locally defined. There's no way that we can broadcast a function to broadcast a defined local function to other processes. So instead, the correct way is showing on the right hand side of the slide. We define a function everywhere. In this case, we define a global function, a function globally everywhere. And then we execute this procedure on every process. Okay, so again, in summary, you used the mechanism everywhere and a statement to broadcast the values or define the functions everywhere. Okay, let me just show you an example. Here, I have Julia already started, and using this distributed. Okay, and then do, okay, I guess I need to quit. And restart Julia using four processes, because I have a 4 cores on this machine. Okay, and using distributed. All right, and I define everywhere function show ID, and this function will just do just print my my ID, and then call my ID, which is a Julia function. And so now this function show ID is defined everywhere. Okay, so now I want to execute this function. I do everywhere, because the function is being defined. If I do show ID, now this show ID is a function that's already defined. If I do show ID, and that just shows the ID of the current process, the control process. But if I do everywhere show ID, then everyone will report the ID. Okay, so this is a broadcasted example of showing broadcast, and define broadcast values and define functions everywhere. Let's continue. So what if you want to, I want to not only execute, do some have a remote processes, workers do some work, but also want to get the results back. How do we do that? And get the results back and save in the variables. And in this case, we would have to use the macro spawn and the spawn at. Okay, and here just shows an example. Again, using distributor, you have to use the package distributed. And then in this for loop, I loop over all the participating workers that I started. When I started Julia, I used the -p and a number of workers. And I loop over all the workers. Workers, by the way, workers is a Julia building function. It returns the number of workers. And then I use the macro call spawn at. Spawn at I is the ID. I want to spawn these tasks, 3 tasks. I want to return ID and get the Unix process ID and get a host name, the 3 tasks. I want to get the 3 tasks and on each of the workers and going from 2 to the number of workers. So by the way, when you start Julia with, let's say with 4 processes, And Julia always starts for +1, or if you start n workers, then you will always have n+1 with the first one as the control process. Okay, so I'm looping over all the workers going from the second, going from the first worker to the end. I want them to report 3 things and a return. Now this spawn at, this mechanism, the spawn at places a thing called a future. Okay, so it's kind of like you place the order. You place the order, and when the order will be delivered, we don't know what will be delivered in the future. So therefore, spawn at, you replace by calling spawn at, you place an order which will return a future, an object called a future. And then you call the function fetch the future, fetch the result back. And the results back will be stored in ID, PID, and the host correspondingly. Okay. And then once we've done that, and we just display the ID, the Linux process ID, and the host name. Okay. To place to run a remote procedure on automatically choosing workers or process, you just put the spawn without the name, without the ID of the remote process, and it will randomly choose the worker. Or if you want to specifically, I want this one, I want the process N to do this work, and then you use the spawn at. So this provides you the mechanism to dispatch a computational tasks to a specific worker. Or if you don't care, you can just randomly dispatch your task to the next available worker. Okay, this is how you use a spawn, the macro spawn, to distribute the work to the workers. Okay, here's another example. There are 2 examples here. I define the 10,000 by 10,000 matrix here, a random matrix, and then I dispatch this work. I want to sum the A square. And here's the spawn any, spawn at, column any, means I don't care which one. Now, the second example, I'm dispatching this instead of an A, but the size to and the random worker, and I have that worker do the same, essentially do the same. The difference between these two is obvious. You create a local object, local matrix, and here, in the first example, this first example involves transfer or copying that matrix, 10,000 by 10,000 matrix, to the remote workers, as opposed to the second example here. I'm only copying the size, which is a single variable, scalar, 10,000, to a remote host, and have remote host to generate a random matrix and the sum and the return. Okay, so because the second one doesn't involve data transfer, so it will be faster. Okay, just a summary. You use the spawn and the statement or the procedure you want to execute on the remote host without the target, and the Julia will just pick a worker randomly. Or if you want, especially when you do the computational work in the managed manner. You want to distribute this amount of work to this and this amount of work to that. And you want to have a target process ID. So you use the spawn at and then the procedure or your computational tasks. And again, this computational tasks in a statement or called a procedure might involve data transfer. For example, in this case, we in the first example, we broadcast that matrix. We broadcast that matrix generated locally and broadcast that matrix to a remote worker. Okay. And what's happening underneath that the data transfer is through MPI or message passing. Okay. Just a little summary on the programming model. Julia always uses a 1 plus P processes here. P is the number of workers or processes that you want to use. Basically, you will have a control or the main process plus P worker processes. This diagram shows that initially your code starts here, the first one, and the rest of the workers will be labeled as 2, 3, 4 until P. And you start off by defining variables and the functions and broadcast them to remote workers or define the functions everywhere. And then the next, you would dispatch tasks to workers. You dispatch tasks to workers. And each call of a spawn is actually place a future on the worker processes. And if you want to get the results back, then you need to call a fetch on those futures or on those orders in order to get the results back. And this is the programming model. And this programming model, the program model here used here is different from the SPMD model. In the SPMD model, one often uses the process ID to control who does what. And here is pretty much a dispatcher worker model. Okay. Okay, just briefly, a remote call and the other Julia functions that I can use. This is a synchronous call. Remote call, you call what function you want to call and where and the variable. Okay, and this remote call will place a order and a work order and call the future. And then to get the result back, you call fetch to get the result back. Next, let's take a look at an example of computing pi in more details in a distributed manner. So what we're going to do here, we compute the approximation of pi by tossing the points uniformly in this square. And we just count the number of points inside the circle and on the circle, and then versus the total number of points. And so this will give us an approximation to pi. This formula shows that. So we just count the ratio, the number of points inside versus total number of points multiplied by 4. That will give us a estimate of a pi. Let's see how we do that. The first, we define a function, which is toss the function that tosses the number of points. Inside this function takes an argument of n, which is the number of points, and then we loop over number of points, and we generate a random, uniformly distribute point x and y coordinates, and then we count them in if they are within the circle. We just do this calculation. Otherwise, we don't count. So in the end, it will just return a number of points inside a circle. And then we write another wrapper function called pi underscore p. This will first we'll get the number of workers we defined, and then just pay attention to the next line. We have a for loop because we want to dispatch the amount of work among workers. We loop over the number of workers, and then with inside this for loop, we call this function points inside the circle, and we apply a macro called distribute to this for loop, and with a reduction operation plus. So essentially what this does is we dispatch this for loop, chunks of the for loop to each worker, and in the end, we collect all the countings of the votes back and add them up and store them in this variable n in. So we have individual workers to count number of points inside. And then we sum them up, and then we get approximation for 4 times this ratio. Why we want to put this thing in a function? The first one is obvious. We want to have this procedure to be executed on each worker. But why do we bother to use this function again? To write a function wrapper. This is because in our previous talk that the Julia uses a just-in-time combination technique. So it compiles the code. If you put the code inside a function, and then the Julia will compile the code, and then the code will be running much faster. It will be much faster than other interpreted language like Python, Matlab, and R. Okay. So again, just a little summary. Distributed operator and procedure. This syntax distributes this procedure to workers if this operator is present. For example, is plus. This is a reduction. This means after this procedure is executed, the result will be reduced through the reduction operation and return back. So it does 2 things in one shot: dispatch the work, the task to remote the workers, and collects the results back and add them up. Okay. Here's an example. I start 4 workers, and then inside the Julia, I use a package distributed, and then I need to define this everywhere, pi, define. This function is, I want to have this function defined everywhere on the workers, and then I just call this a function wrapper, pi, and to get this result. Okay, so I do a Julia dash P4. I want to start 4 processes, so 4 workers. And then if we do n procs, it will show I have a 5. Okay, I have a 5 Julia processes. If I do workers, and then it will show the IDs of the worker processes going from 2 to 5. Now, I'm going to use distributed, and then do everywhere I want to define a function. Now, the function is already defined and saved in the file. So then I want to do everywhere include. This is a Julia syntax to include a function. If you ever already have a function defined and it's saved in the file, then you can do include the loader function. So the function, the file is called the dist GL. Okay, so this function is being loaded, and it's loaded everywhere. So, and then I can simply just do a pi, because there's a pi underscore p is already defined in that file. Now I want to do give it 100,000. So in Julia, you can use underscore to separate the integers to make it more readable. So I want to use 100,000 points. 100 points. That's not good. Let's do. Let's put the timer around. P. What about 1 million? Oops. Now it's getting a little better. What about it do this? It will take some time, and hopefully we'll get a better result. Yes. Now, just warn you, if you don't have enough cores, don't go 4 3 zeros. Okay, and that will take lots of time. Okay. So this time it take 2.8 seconds. If you multiply that by 1,000, and it's going to take almost an hour to finish. So don't do that. Alternatively, we can do this pi example slightly different. So on the left-hand side, we still have the tossing the points, function points inside the circle. But on the right-hand side, we are using a slightly different approach. In this function wrapper, instead of using distributed macro, we're using a Julia function Pmap. The Pmap is a Julia function that maps an array of tasks to workers. Okay, so the syntax here, the first argument, the Pmap, the first argument is the function, and the second argument, which is the square bracket, that's the array. That's the array of elements, which basically is the number of points. Okay, so for example here, if I do say P is 4 and the N is 1,000, so 100. If I do N divided by P and do a for loop, one goes from I goes from 1 to P. So it will just return 4 elements. Okay. So this square bracket will return 4 chunks of, in this case, basically just 4 numbers. And these 4 numbers will be taken and will be mapped by Pmap to 4 workers. And that the Pmap, it will return the result. And then locally, we just run the sum and get the number of points. So that's just a different way, another way to execute the procedure remotely and get the results back. Okay, that's just a quick example of showing using a Pmap function, a map reduce function. Map function maps a array of elements and execute a function on each of those elements. And the Pmap does the same, but it does one step further. It maps the elements to the function, and also it distributed the uh, the uh, the amount of work to different workers. Okay. All right. Next, let's take a look at using a distributed arrays. This is a feature supported by Julia packages that make a computation on distributed memory machines much simple. So here's the example. A matrix is stored across four processes on a 2x2 Cartesian processor grid. So what we have here, process one has the blue portion, and process, now worker two has the blue portion, worker three has the green, and worker four has the yellow, and worker five has the pink. Okay, so I have this matrix, this A by A matrix, and I want to have a sub matrices, four sub matrices to be stored on this 2x2 processor grid. So how do we do this? We use distributed package and the distributed arrays package. And I'm just loading linear algebra package everywhere. So everywhere we'll have the linear algebra package loaded. And then I define the function AA. The AA is basically create the elements on the diagonal submatrix. And the B1 creates the submatrix on the off diagonal. On the off diagonal, which is here, okay? And the B2 is also on the off diagonal, which is here. Oh, so B2 is here, B2 is here, B1 is here, okay? So I define these functions everywhere, AA, B1, B2, basically just create the submatrix, diagonal and off diagonal, okay? And the next, once I have these functions defined, then I just call AA. I just call these functions to create those submatrices on the corresponding workers. I call spawn at on 2, and the 3, and 4, and the 5. And each one of them will return not the submatrix, but a future, a reference. Okay, so here D1, D11, D11 correspond to the diagonal matrix, D11, D12, D1, D21, D22. They are not matrices, they are simply references. Okay. And then I'll create a distributed matrix. I'm ready now with the references D1, D11, D12, D21, D22. I'm ready to create a distributed matrix on this 2x2 processor grid. How do I do that? I simply just by calling DA equals. I call the function DArray, which is the function inside the package distributed array. And this distributed array will generate a distributed matrix, this distributed matrix with these references, with the portions, data portion references to by these references on a 2x2 grid. So in other words, this D array dimension distributed matrix, again, is a 2x2 block matrix. This generates a 2x2 block matrix. This 2x2 block matrix, again, this DA is a reference to the 2x2 block matrix and not the entire matrix. Okay. So the next, I guess I better just do do the example here. Show the example here. I need a open another window. Another window here. Okay, so I'm just cheating. I need to look at the code. So first, I'm gonna do these. I need to define the function A, B1, B2. These are the block matrices. I just load it up here. Oops. Copy. Okay. And then I create a submatrix on each processor. Now, in this case, I want to, now I do a little bit, it's not the 4x4. Each submatrix is 100 by 100, so make it a little bit larger. Okay, as you can see, there's a D11, D12, D23. They are not real matrices. They are future, a reference point. Okay, and then I create this 2x2 block matrix. Once I have these elements ready, D11, D12, D21, D22 ready, I'm ready to create this 2x2 block matrix. And after a little while, this matrix is being created. This will be a 200 by 200 matrix. Okay. And then I define this. I load the package. I load the package interactive util. And in this package, there is a var info function. Var info function, let's see what var info function tells us. So run the var info function examines the variables in the local process. As you can see here, our DA is a distributed matrix holding a 200 by 200, 2x2 block matrix. Now, this is the amount of the memory it takes is 544 bytes. But the real matrix it's a 200 by 200 matrix. Is definitely is not the 5 by 5 bytes. It will be 200 by 200. It's a floating point. It's double position times 8. That should be this much amount of memory. So this tells you that this object, the DA distribute array, does not take that much memory. Okay, this is only this is a metadata. This is how much memory it takes, and each process, each worker will have the actual data. Okay, now the var info only shows the variables inside inside this current process. So what if so what about the workers? We want to see that the situation, how much memory it takes on workers. Again, as you can see, the D11, D12, D21, D22, these are the futures. These are the references. They don't take much memory locally. So what if I want to see the how much memory each worker will take? For example, worker 3. So I can simply run not everywhere. I want to span at worker 3, and I want to run var info. Oh, sorry. Then I want to fetch the result back, because SpawnAdd only place an order. So this shows the how much memory actually used on the remote host. Variable 3. Okay. And if you want to do 4, okay, so you can find the information on the remote host. Now, let's take a look at, now, as I said, the DA is not the entire matrix, but it's a metadata. But what if I just type a DA? What I'll see? Oh, that's too big. That's not. So it, this is not good. It's too big. Let's do it again. I want to run a smaller case. So this DA, oops. Make it smaller. Okay, so even though the DA here, as I said, is a metadata, it's just a reference, but you can still use it as if it were a matrix. Okay, you can use it directly as a regular array. So if I do DA, let's say on the diagonal 5, 5, it should return this element. That should be 2. Yeah, that should be 2. So if I do 5 and 4, which is this element, that should be -1. It should be -1. And as well, we can do matrix multiplication directly on this distributed array. And this is the whole point. We have the array distributed, stored and distributed, but we should be able to apply the operations on the distributed array. Yes, this is verified that we can do, for example, the matrix multiplication directly. To verify that this is correct, let's just create a local matrix. Okay, a local 8x8 matrix, which will be the same. So this is a local matrix. This is identical to the elements are exactly the same. This is A, which is local. This is a real matrix, 8x8. And here DA is a distributed matrix, distributed across the 4 processes on 2x2 grid. And if you do a matrix multiplication, that should give you the same result. If you do DA times DA, that just verifies that you can do linear algebra operations directly on the distributed array. Okay, so let's move on. A quick summary that we can define the functions to be executed on the workers using everywhere. And we can create a distributed array by calling functions. And we can perform operations on distributed arrays. And this is a very different concept from SPMD model. And in this model with the distributed arrays, you have access to the global space distributed across processes, which make your mathematical computation, we're writing the code much easier. You don't have to worry about the data transfer between processes and where the processes are, the topology of the processes. All you need to worry about is entire abstract data set. For example, in this case, it's a matrix, the matrix. The matrix is stored, distributed across different processes, workers, and you can do your computation as usual as if they were stored locally. Okay. Okay. So next, similarly, there's the feature shared arrays. With the shared arrays, then you can so shared arrays. Shared arrays, by its definition, by its name, it means that if you create an array, then this array will be visible, will be shared by all the other workers. Okay, so in this case, I create a 5x4 shared arrays, and then the A becomes available to all the participating processes. Here's example. Here's example because A is a shared. A is a shared. So if you change if you change A on one worker, then the change will be visible to all the other workers. On the left hand side, and the A here, the array A is defined local. And in this example, I distributed, I'll assign the values to A in a distributed manner. And then the A is available on other workers. Here's the key point. Using distributed macro, you're broadcasting an A to other workers as well. However, the way the distributor works here is on each process, the assignment that the amount of work is only done locally. So in other words, you will not see what's happening elsewhere because A is local. Even though the A is being distributed to other workers, but each one gets a copy. As opposed to the right-hand side here, we define A as a shared array. Now, once we define A as a shared array, this A becomes visible to all the participating workers. Again, if I do distributed, apply the distributor to this for loop, and this A is now that everyone gets values assigned. Okay, so each process has access to the entire chunk of an array. It's not like the example on the left. On the left, A is local again. And here on the right-hand side, if you're using shared array, A becomes global. And every worker has the same view of this A. Okay. Lastly, let's take a look at an example using threads. We're not going to cover threads today. It will be a separate topic. We just want to show how easy it is to use threads in this case. So given a set of observation data as shown in the blue dots in the diagram on the right, we use a given model f of x containing 8 parameters to fit the data. That is, to define the parameters that best fit the data in the least squares sense. And we're going to use a Monte Carlo method to do so. This is a toy example. The purpose is to show how we implement it in Julia and how to perform parallel processing. Here's a sketch of the algorithm. First, we generate endpoints of P, where P has a dimension of 8, with each element of a P uniformly distributed in the corresponding dimension within its range. And for each point P, compute the error Z, and we store Z in an array. And then we sort Z in ascending order, and we pick the first m corresponding points, P, as a new candidates, and we find the minimum Z. And then we just arrange for each dimension of P that encloses the m selected candidates. And then we continue. If the stop criteria are met, then we stop, and otherwise we continue. So here, let's see how we translate the algorithm into Julia code line by line. So first, we generate the n points and the n vectors of parameters and store them in a d by n array, where d is the dimension of the parameter. That is 8 in our example for later selection. And in the meantime, we calculate the norm of this distances between the data and the model at each of the observation points. And we store the values in array Z. And then we sort the Z in ascending order by calling Julia function sort perm. It returns the indices of assorted elements. That is what we want. And by the indices of a sorted array, we find the corresponding vectors of the parameters. We pick the first m of them as the candidates. And we use a view of the m selected column vectors from the d by n array instead of referencing it to it directly to avoid a memory allocation in Julia. And we update the range of each of the parameters based on the m selected candidates referred to by the view by calling Julia function minimum and the maximum. And then we continue. Now, let's take a look at the actual code and the test runs. So here in the text terminal, we started Julia. And I just copy and paste the initialization to load the data into Julia console. Well, basically what I'm doing is just load the observation data points and set the number of points and number of parameters. Okay, and here the number of points is set to 10,000. Okay, so it's at 10,000, and the number of iterations. Okay, let's set to 10. Okay. So first, let's take a look at what the observation data will look like. It takes a little bit time to load the Julia plot function package plots. Okay, it's ready. Then we call the function plot x and y, which are the observation data. In a few moments, you will see a diagram appear. Okay, so this is the diagram of the observation data. Let me just make it a little bit bigger. And then we just performed iterations. Copy and paste it here. And we will perform 10 iterations. Okay, as we can see, as the iterations goes on, as we iterate through the process, the curve changes up and down. Okay, let's change the number. Let's increase the number of points to 100,000 and run the iteration again. Now, this time, it looks like it's getting better. And we increase the number of points to 500. And hopefully we can get the curve to fit observation data better. So 500,000. And we run the iteration. Well, this time it will take a little bit more time to run. As you can see, each iteration takes more time. But as the curve is getting closer to the observation data, and as you can imagine, if you use more points, then and hopefully then we can get a better fit. But it will take more time. Let's see how much time it takes. Now this time it took 36 seconds for 10 iterations. Okay, so 36.7 seconds for 10 iterations. Now let's take a look at the iterations. So here is the main loop of iterations that we just showed in the slides. Here's the loop of iterations. And the first, we generate the n points of vectors of parameters. And then we calculate the distance between the model and the observation data. By the way, I have a threads in front of this for loop. I'll come to that just in a few moments. And then after we calculated the distance and stored it in Z, we sort array Z by calling a Julia function sort perm. And it returns the indices of a sorted array. And then we take the view, and then we take the view, and then we adjust the range of parameters in each dimension, and then we continue. And the most of the time is actually spent here generating the n points of vectors of parameters and calculating the distances between the model and the observation data, and the rest take less time. Okay, so how are we going to speed up this process? We want to thread this loop. We want to thread this loop and see if we can reduce the execution time. So how do we thread this loop? We simply just put the add threads in front of the for. When we did the test run here, we only used one thread. So effectively, we're just using a single thread. In order to use multi-threads, so we need to start Julia with the option -t and the number of threads. Now, on my computer, there are 4 physical cores, so I would just use that up to 4 threads. If you have more cores, then you can certainly you can use more threads. So I started Julia in 4 threads. Okay, so we come to the Julia console, and then we just we load the code again, load the data. Load the data, and the plot function package, it just takes a little bit of time to load. Okay, and the plot, XY, and we We just plot the observation data. Again, it takes a little while to generate a graph. Okay, we don't need this. We only need this. This is our new one. We don't care about the old one. And then we want to set the number of points to 500,000, as we did in using a single thread. And then we want to set the number of iterations to 10. Okay, and then we run this iterative process. Bring this up back here. Now, as you can feel, like this time using 4 threads, it is running faster. Let's see how much time it takes. Okay, so it took 19 seconds as opposed to 36 seconds. Let's run it again. Okay, 15 seconds. So this is the best result that we can get. Okay, so in conclusion, oh, by the way, notice that there's some overhead in memory allocation and the garbage collection. So that's why using 4 threads, we didn't cut the execution time to 1/4 of 36 seconds, but we did reduce the execution time. So as you can see, there's some overhead, and this is something yet to be discussed in a separate talk next time. So in summary, to start a Julia in threads, and there are 2 options. You can type a Julia dash minus T, the number of threads, or Julia, let me just quit. You can do a Julia dash T 4 threads, or dash dash threads and the 4 to start 4 threads. Okay. Yeah, I should stop here, and we open the question to the audience.